Hey everyone, so today I'm going to talk about a geometrical viewpoint for a linear transformation. So in earlier lecture, what did we see? We see that what is a linear transformation and we saw some of the examples. Today we are going to see geometrically, and it's always good to see some things geometrically because it develops our interest in that, right? So let us try to see some geometrical viewpoint for a linear transformation. So just for the sake of a completion, what is a linear transformation? It's a function from one vector space to another vector space which satisfies two nice properties. One is with respect to addition and one is with respect to scalar multiplication. So if a bar and b bar are two vectors in a vector space V, then t of a bar plus b bar is t of a bar plus t of b bar, and t of alpha a bar, where what is alpha? Alpha is some scalar. Now you can take alpha to be a real number, and if you are comfortable with arbitrary field, then you can say that alpha belongs to a field. But it's okay if you don't know the concept of field, you can take alpha to be a real number. Then t of alpha times a bar, where a bar is in V, is alpha times t of a bar. So that's what we have seen in the last lecture. You can refer that lecture for your revising purpose. So now suppose, let's go to some special cases. Now suppose T is a map from R2 to R2, and let me define T. If you take any x comma y in this two-dimensional space, output is x comma minus y. One can write x comma y goes to x comma minus y, but whenever we are in linear algebra, we always represent vectors as a column vectors. Okay, that's why column representation. Now you can see, now homework for you is verify that this map is a linear map. Okay, you should be able to do it. So this is a linear transformation. Now let us try to see this geometrically. Now what is happening? Now there are two ways to visualize this. One way is you draw this R2 to R2. Now if you take any point, suppose if you take 2 and 3, if you take 2 comma 3, what will be the image? It will be 2 comma minus 3. Because as you can see, my first component, which is x, it is remaining same under the map. Whereas what is happening to the second component? There is a change in sign. Okay, so if you have 2 comma 3, it will go to 2 comma minus 3. Okay, if you take minus 1 comma minus 2, its image will be what? X is fixed, so minus 1 will be there, but minus 2 will become plus 2. Okay, so if you can take some couple of points. You can pause the video if you wish, and then you can take some more points, and what you will observe is under this map, the points in the upper half plane are going to the lower half plane, and the points which are in the lower half plane under this map, they are going to the upper half plane. So all these points over here, will have image over here, and all these points over here will have images in the upper half plane. So that's why this map is called as a reflection along x-axis or reflection along y equal to 0 line. Okay, because you can see, and if you take any point on x-axis, its image will be on x-axis only. Because if you take any, say 1 comma 0, image is 1 comma 0. You take 2 comma 0, image is 2 comma 0. You take minus 3 comma 0, image is minus 3 comma 0. So on x-axis, it is an identity map, or you can see the points on x-axis remains on x-axis. So when you do the reflection along the x-axis, since I am reflecting along this line, points on this line remain there only, and only the upper and the lower half planes swapped each other. So this is called as a reflection map. To be precise, reflection along y equal to 0 line, or reflection along the x-axis. Now another way to represent is you draw in a single diagram. Okay, don't draw two diagrams. For early stagers, they can take the help of two diagrams, but once you are comfortable with this, you can consider only one diagram. So what is happening under this map? The reflections is happening. Okay, so suppose for example, if I take a square over here, I have a solid square over here, and if I want to translate, or if I want to shift this over here in the fourth quadrant, so while doing the coding, what function I will define? I will just say x comma y goes to x comma minus y, and under this map, when I execute my program, the image of the circle will come over here, image of a square. If you don't like square, you can take any object, like if you can take any cartoon object. Usually people in animation industry, they play with the objects. This has a very wide application in computer graphics. Okay, so graphic industry mein this is used a lot. So suppose if you have an elephant over here. Okay, so I'm trying to draw an elephant over here. Very bad drawing. Okay, but I tried to draw an animal, but okay, you can just assume that this is some object over here. And if you want to see its image over here, what you do is you just apply this map. So what will happen is this point will map over here, this point will map over here, this point will map over here. So it will just get reflect like this. So his head will come here, legs will come here. So this is nothing but a reflection map. Okay, so that's another way of looking the diagram in once looking the map under single diagram. Another way to write this is in terms of a matrix. Now if you can observe, I can write this as, since there is x, so I can write 1 0 and there is minus y, I will write 0 minus 1. You do this multiplication, you get the same thing. So another way to write this is T of any a bar is a times a bar, where a is this matrix, a bar is a vector, say x comma y. So this is a matrix representation for this map. Now suppose you want the reflection along y-axis. Okay, so you have some object over here and you want its image over here. So what function you will define? So for reflection along x-axis, my x component was fixed. Now I want to do the reflection along y-axis. So my y component should be fixed, right? So I simply define the map as x comma y goes to minus x comma y. Matrix wise, this will be minus 1 and plus 1. Okay, so now you can see the images of few points. Now what will happen is this will reflect the points along y-axis. So the points which are on the left half of the plane under this map will go to right half of the plane, and the points which are on the right half of the plane under this map will go to the left hand side of the plane. And whereas the points on the y-axis will remain on y-axis itself. Okay, so if you have some object over here and you want to simply reflect along y-axis, you define this map and you get the answer. So here is a first set of homework for you. So take this map. Now xy is going to y comma x. Okay, so just replace x by y by x. So now just to try to see that which points will have the same images. And from here it is very clear, when x and y both are same, my output will be same. For example, 1 comma 1, output is 1 comma 1. 2 comma 2, output is 2 comma 2. Minus 1.5 comma minus 1.5, image is again the same thing. So you can see points along the line y equal to x line, they are having the same images. So from here one can have the intuition that this map is nothing but the reflection along y equal to x line. So you draw y equal to x line and the objects will get reflected along that line. Okay, just try to see this. Tell me what about this and what about this. So this is a reflection along a line which I already gave you a hint or almost a complete solution. This is also a reflection along a line, and I think this is reflection along a point. So tell me in the comment section, this is a reflection along which line or along which point. Okay, now we are done with almost kind of a reflection thing. Now let's go for the rotation part. Now suppose you have some object over here, some animal over here, or some any cartoon character or anime character. Now what I want is, in the next scene, I want this object to be over here. The same thing along the y-axis, positive y-axis. That means what? I need to rotate this by what angle? By 90 degree I should be able to rotate this. So for that, what map will help me? Okay, so for that we define the map T of x comma y goes to 0, minus 1, 1, 0 times xy. That means x comma y goes to minus y comma x. Now you can see what is the image of 1 comma 0. Image of 1 comma 0 is 0 comma 1. Okay, image of, if you take 0 comma 1, so 1 0 goes to 0 1, 0 1 goes to minus 1 0, minus 1 goes 1 0 goes to 0 minus 1, 0 minus 1 goes to 1 0. So you can see all the points will get rotated by 90 degree. So if you plot the images of each of these points, it will get rotated by 90 degree, and this whole image will become like this under this map. Okay, so that is one way. Another thing, like if you want, now question is, this is rotation by 90 degree. Okay, now if I want to rotate by some other angle, in general, if you want to do a rotation by any particular angle, suppose you want to only rotate by 45 degree, then what should be the matrix? If you want to rotate by 120 degree or 180 degree, then what should be the matrix? Is there a nice formula? Answer is yes. And the answer is, it's simply cos theta sin theta minus sin theta cos theta, where theta is the angle over here. So you take an angle. So here I put x theta equal to pi by 2. When I put pi by 2, it is 0, minus 1, 1, 0. If you want to rotate by pi by 4, 45 degree, it will be 1 by root 2, minus 1 by root 2, 1 by root 2, 1 by root 2. Okay, so this is a very nice formula if you want to rotate an object by a certain angle. Okay, so this is about the rotation matrices. It rotates an object given a particular angle. So that's why this matrix is used a lot. Okay, suppose you want to, one can also do composition of linear transformations, or you can say the matrix multiplication. Suppose I want to rotate first by 90 degree and then I want to reflect over here. So I want this image to be like this over here. So one way is one can simply rotate in clockwise direction, or one can do composition of maps. That means one can first rotate by 90 degree and then you apply the reflection along the x-axis. Okay, so like you first multiply by this matrix 0, minus 1, 1, 0 to the given points. The image will come over here. Then you apply what? Then you apply the reflection one. What was the reflection matrix? It was x comma minus y, right? So 1, 0, 0, minus 1. So if I define a map T of xy like this, then what this will do? First you rotate and then you reflect. Okay, so composition of linear transformation, doing the composition of a linear transformation is same as to do the matrix multiplication. And that's why we always try to relate a matrix with a linear map, because playing with a linear map becomes quite difficult once we have a different maps, but matrix multiplication is ultimately very easy. That's why that's why one should able to write a matrix for a given map. That you will be studying in the coming lectures, but yeah, this is about the composition. So we are done with the rotations, reflections and the rotations. Now let's go for some different kinds of geometrical transformations. So now the next set of matrices are nothing but the contraction or the expansion matrices, or the contraction or the expansion linear transformations. Now suppose if I have a square over here, this is a unit square 1, 1, and what I want to do is I want to define a map so that it gets contract. Okay, like this. So there is no change in the height of y, but suppose the height of x or the length is becoming, the length of x is getting cut by half. So I want this as an image. So I am contracting. So what I will do is I will simply multiply. I will not change y because there is no change in the height of y. There is a change in the length of x. So I will simply reduce it by half. So I will just take half into x. Okay, so x comma y goes to x by 2 comma y. So you can see 1 comma 0 will go to half comma 0. Half comma 0 will go to 1 by 4 comma 0. 1 by 4 comma 0 will go to 1 by 8 comma 0. Like this, all these points will get shrink by half units, whereas the height of y is remaining same because there is no change in the y component. So x comma y goes to x by 2 comma y will contract the square like this. In general, if I want to contract the square by some amount k, where k is between 0 to 1, because when k is 1, it is the identity map, square will go to exact square. When k is 0, it is 0 comma y. It's a kind of projection map. We will come to projection maps later on. So that's why I'm taking between 0 to 1. So whenever I take a number between 0 to 1 and multiply by x, obviously this value k into x will be less than x. Therefore, what will happen is the contraction. And if my k is greater than 1, then what will happen is the expansion. So for example, x comma y is going to 2x comma y. So 2x comma y. So y is remaining fixed, but x is getting multiplied by 2. So 1 comma 0 will go to 2 comma 0. In that case, I will get then expansion, I will get a rectangle. Okay, so this is the thing that we'll usually see. So when k is between 0 to 1, this is called as a contraction map, contraction along the x horizontal line. And when k is greater than 1, it is nothing but the expansion along the horizontal line. Okay, so that is one thing. And if you take the negative part, minus x, okay, then it will go like this. It will just go expand or along this side, left hand side of this square. Okay, so that was one thing. Okay, now suppose you want to do other way. Now suppose you want to find an image of this. Now x is remaining same, but height of y is decreasing half. Earlier was the x was decreasing by half, my y was fixed. Now my x is fixed and y is decreasing by half. So what map should I use? The same thing. Now for that x comma y will go to x comma y by 2. So I am keeping x fixed and I am reducing y. So this is the map I will take. Okay, and in general again the same thing, x comma ky. When k is between 0 to 1, it will shrink like this, and when k is bigger than 1, then it will expand like this. So whenever you want to do whenever you have a character which you want to just shrink or which you want to expand in the animation or in the cartoon thing, then people use this kind of transformations for expansions and the contractions. Now the next set of geometrical transformations are the projection transformations. Now these are called as projection maps. Why? Because suppose if I take 1 comma 1, what is the image of 1 comma 1? It is 1 comma 0. What is the image of 2? If I take 2 comma 3, what is the image of 2 comma 3? 2 comma 0. What is the image of minus 1 comma minus 2? Minus 1 comma 0. What is the image of say minus 2 comma minus 3? It is minus 2 comma 0. So if you take any point on upper half plane or the lower half plane, under this map the image will always lie on the x-axis. Image will always lie on the x-axis because the second component is becoming 0. So I'm just projecting this. Okay, so this is called as a projection map, and to be specific, projection on x-axis. Okay, similarly if you want to projection on y-axis, okay, if you have 1 comma, if you have say 2 comma 1, you want to project on y-axis. So what map you will define? You will define x comma y goes to 0 comma y. So 2 comma 1 will go to 0 comma 1. If you take over 3 and say 5, 3 comma 5 will go to 5 comma 0. If you take over here minus 2 comma minus 3 will go to 0 comma minus 3. So this map will give the projection on y-axis, whereas this map will give us the projection on x-axis. And usually projections are required a lot. And the same thing gets extended in higher dimension. Higher dimension is in, suppose if you take a map from R3 to R3, okay, so x, y, z going to x, y and 0. So this is a projection on xy plane, okay, because z component is becoming 0. If I define a map x, y, z is going to x, 0, z, then this is a projection on xz plane. And similarly 0, y, z, that will be a projection on yz plane. So let's suppose if you observe a donut over here, you have a donut, and if you see its projection, so if the floor is xy plane, so I have a donut, and if I project it on the xy plane, what I get? I will get this annulus circle, right? That will be the projection of a donut in xy plane. But the same donut which I have, okay, if the bottom x-axis, y-axis and z-axis is here, okay, if this is my y-axis and this is my z-axis, so this plane is my yz plane. So I have a donut and I project it on yz plane. So that donut will be projected like this, and what I get is over here is a segment like this. So projection will be a segment. You just stick that donut over here. So it will just project like this. So that circular arc will come over here and you get a strip like this. So projection differs on which plane you are projecting. Again, this is a very vast topic which one can give lecture for an hour. But okay, I just want to give you the idea about the projection map. So these are the projection maps. And the last set of category comes is the shearing, S-H-E-A-R. So let us try to see that last part. So what are shear maps? Suppose I have a rectangle over here or a square over here. You can take this as a unit square. And I want to shear it, or I want to do like this. Okay, or I want to shear like this. Okay, so I just want to tilt here or tilt there, something like this. So again you can see my x is getting tilted that side. My height is same, 0 to 1, 0 to 1. But x is, suppose this is 2, this is 1. Okay, so you can see height is fixed. There is a change along this horizontal part because I am going towards that side. Okay, so x comma y, you can, from here you can see that my y component is fixed. x is tilting, so I'm adding something to x. You can see 1 0 is going to 1 0, 1 1 is going to now say 2 comma 1. Okay, so I will just define this as x plus y. So you can see 1 0 goes to 1 0, 1 comma 1 is going to 1 plus 1 comma 1, which is 2 comma 1. So this is just shearing towards the right side of the x. Okay, if I want this to on the left side, same thing, you just multiply with some multiple over here. Okay, so if you do such kind of addition or subtraction like this over here, then what will happen is shearing of the objects. Okay, so this is last thing called as shear. Similarly, if you want to do the shearing in the y part, you want to keep the x, like here this base was fixed. Suppose if you want to keep this as fixed, okay, you want to do like this. So this is fixed, but this is changed like this. Or similarly in the bottom you want, then you do the shearing along the y component, you keep your x component fixed. So these are the basic geometrical transformations for 2D. I have not touched the 3D part, but yeah, these are some basic transformations which is good to understand or good to realize at the starting stage of when you study linear transformations. Also, these are very famous maps, reflection maps, rotation maps, then shearing maps, projection maps, and contractions or the expansion maps. So I hope all these maps are clear. If you have any doubt in any of the maps, you can ask me in the comment section. Thank you.